Well, if you looked at problem 8 of magnetic forces on currents in the Webb assign, there's a good chance you were a little confused, and therefore I want to reduce the confusion and solve the problem for you. And to do that, I'm going to kind of need to start by drawing a picture of this thing, which is not my strong point. But we have a loop of wire. Okay, here's a loop of wire, actually a segment of wire there. And it is from the vertical here, it is at an angle of 30 degrees. See if I can do this. I want to make a parallel line from here now. Okay, that's about as good as I can possibly do with my very limited artistic abilities. This is a complete loop of wire with a current flowing like this. All right, I'll just draw an arrow like that. This is I. I is flowing in that direction. So it's flowing down here, it's flowing here, flowing around in this direction. This is a 30-degree angle, and we're given that this is 8 centimeters, this is 8 centimeters, this is 6 centimeters. Well, we want to figure out what orientation of magnetic field we need passing through this coil. And by the way, this is the y direction, and this is negative y. And it's either going to be y or negative y, vertical, up or down, that the magnetic field is going to be. In order to get this wire to pivot from where it originally was down here, it's going to pivot 30 degrees. All right. So that seems a little like it should be real simple, but essentially, what we're going to do is look at this in terms of torques. All right, so the way we're going to look at this is to say that the torque clockwise is equal to the torque counterclockwise. That should be fun, and that's familiar ground for all of us. So the clockwise torque would be the torque, and again, that's not vector direction, but gravity is trying to spin it down this way. And at the same time, with the magnetic field, along with the interaction with current, that's trying to rotate it out the opposite way. So the clockwise torque, I'm going to do this now. I'm going to say, this is the gravitational torque. This is kind of like torque gravity, torque electric, if you will. There's an electric or a magnetic, maybe I should say magnetic, since that's the main topic here. They're related, but the magnetic force producing a torque counterclockwise, gravitational force trying to make it go clockwise. So, to get this a little bit more concrete, R cross Fg, that's the clockwise gravitational torque, is equal to R cross Fe, or F, I keep saying E, which is okay, but B, magnetic force, gravitational force, magnetic force. So the first part should be pretty easy. What's the orientation of the magnetic field to do this? Well, you take here, let me zoom out a little bit if I can. So I'll see, use my hand, there's my hand. And the hand's either going to be vertically up or vertically down. Well, the bottom line is we need the force, we need the FB force to be in this direction. We need FB to be in that direction. That's the positive X direction. So your palm is going to point this way. The palm's going to point, instead of me trying to do it, let me just zoom back in here. Palm is this way. The fingers are either going vertically up or down, but the thumb is going in the direction of the current, which is this way. So that's what you need to do. Stick your thumb in this direction. And when you do that, with your fingers either vertically up or down, with your palm has got to be out, so that makes only one solution, and that is fingers have to be up, thumb in the direction of current, then the palm force. I moved my hand around. The video's got to look insane, so I'll try and stop doing that. Your palm is pointing in that direction. So the B field is upward. So our job now is to figure out what the size of the B field is to produce this condition. And it looks like it's going to take me a while. I'm already several minutes into it. All right. So to carry this out now a little bit more, we're going to do the gravitational torque. And if you remember, okay, we got 3 segments here. So what's the gravitational torque? Well, what we got to do is actually find the center of mass of this system. Now, since it's pivoted from this point, this chunk doesn't matter, but these 3 chunks do. And these 2 have a center mass at 4 centimeters, and with respect to this pivot point, and this one is at 8 centimeters. So we need to put that together. But let me, so that's in the background, okay, because we're gonna, at this center of mass, we got FG acting down. And then we have this distance here, which is the perpendicular distance from the pivot point to the line of action. So the torque is this distance times this force. That's key. Let's see, let me focus this here a little bit. Boop. No, okay. So let me write this expression a little more explicitly now. Distance to center of mass, that is the R part here. And then the force is mass times gravity. Excuse me. Cross product is really force and moment arm here. Well, the angle between the radius line and the force is 30 degrees, so it's sine of theta, sine of 30 degrees. So dm mg sine of 30 is equal to, now we need to make that equal to the magnetic force, which is R cross F. Well, the magnetic force occurs here, so it's 8 centimeters along here. That's the R. However, since it's up like that, from this pivot point, we do not have 8 centimeters. My drawing's kind of bad. This should go down like this. It's pivoted up, so this is not, this 6 centimeter line, which has the magnetic force on it, is not 8 centimeters from the vertical. All right, it's less than that. Does that make sense? So let me write the 8 centimeters. So 0.08 meters. And then cosine of 30, because that's the location. Okay, the perpendicular location of this wire from the pivot point, like this, is 0.08 cosine of 30. So you got to be careful with that. That's easy to mess up on. And then the ILB force. So I'm going to go ahead and write IL, and it's really cross B. So I'll say cross B. All right, but the current and L in this direction, the B field is vertically upward, so that's 90 degrees. So that's just sine of 90. So this is just ILB. IL cross B is just ILB. And there it is. That's our equation. So let me go ahead and say then that therefore B, which we're trying to find, is equal to, there it is. So it's distance to the center mass, mg sine of 30 degrees, all over 0.08 cosine of 30, I, and everybody has a different I, right, times L. The L is this. This is L, okay? L is this here, and that's 0.06. There we go. Now, just to clarify, and probably haven't done this yet either, we know that the ILB force on this goes in this direction. What about on the near side here? Is there a force on that one? Well, if you put your fingers upward, so fingers in this direction, with the current going, okay, so it's basically, I know it's down, but it's also across. So put your thumb in this direction. Put your thumb in the X direction. and then with your fingers up, you'll see the palm is pointing, causes a force outward like this. So there's a magnetic force outward here, and for like considerations over here, there's a magnetic force like this. But that doesn't produce any torque. That tries to stretch the wire out this way and this way. It does not produce any torque. Only this one does. So we really have this ILB force on this is the force, perpendicular distance, 8 centimeters, cosine of this angle, gives you the magnitude of the torque. So this is what we have to solve. And now I'm going to take a detour real quick to look at the center mass thing, because that's a little tricky. So we have the 8, we have the 6, we have the 8, and we know that the center mass is somewhere here, right? There's some symmetry. So somewhere along here is the center mass line. We need to figure that out. So it's the center mass is equal to the sum of the xi ri's over the over all the x's, I'm sorry, I didn't mean x, I meant miris over the mi's, not the sum of them. I'm trying to say this. If you need to do the mass times radius of each one and divide it by m total. I'll say it like that. Thinking of a better way to write that. In any case, let's go ahead and carry this out. We have, the problem said, at least for mine, might be different for others, is 0.21 grams per centimeter. So 0.21 grams per centimeter. I'm looking at this one here right now, this line here. It's 8 centimeters. I'll go ahead and just write 8 instead of 0.08 because centimeters should all divide out. But the location of the distance from here to the center mass of this particular leg is, this particular wire is halfway. It's at the halfway point. So it's 4 centimeters plus 0.21, which is the density, basically linear density of the wire, times, it's symmetrical on the other side, so we have 8 times 4 again. Now, how about this one? Plus 0.21 grams per centimeter at a location of 8 centimeters, and it's a length of, I probably should have done that the other way around, but 6. So 0.21 times 6 is the mass, 8 is the location from that pivot point. All that over 0.21 grams per linear centimeter times 8 plus 8 plus 6, the entire length of all of this mass. We don't have to worry about this chunk. There's no torque considerations there. All right, so that gives us, this whole thing, I believe, is 64 plus 48 all over 22, which is 112 over 22, which is 5.1 centimeters. Wow. Okay. Now let's go ahead and finish the problem and be done with this thing. Therefore, B is equal to, stick everything in here now, distance center mass, 0.5051, times mg sine of theta. So the mass, sorry here, but 0.21 grams per centimeter times 22 total centimeters times 0.001 kilograms per centimeter. So this whole piece of garbage here is your kilograms. It's proper units, right? Then we have to multiply by that by g, which is 9.8, and then sine of 30, which is 0.5. Whew. All over this. So we got 0.08, and we have cosine of 30, which is 0.8 something, right? I'll just write it as cosine of 30. Stick that into the calculator. Then we have the current. Now my current in the problem was 8.4 amps. And then we still have the length of this, which is 0.06 meters. And there's a whole bunch of junk. This comes out to something like 0.0015, actually 115, over 0.0349, which is 0.033 Tesla, which is the answer that I get for my particular example, which is correct. And a lot of little places along there where we can go awry, go astray. But hopefully that clarified how to do that. And if you follow this all the way to the end, I'll just make a note that we will have a quiz that incorporates these same principles, even though it will be easier than this particular problem. Good day.